which side of this board is scarier seems to you. Actually, it depends person by person. If you think this side is scarier, you are a normal person. But if you think this side is more scary than this, then you are a physics psychopath. Just kidding for the first purpose of this video. And for today's video sake, it doesn't matter which side seems more scary to you. But what really matters is that if you really want to understand all these four Maxwell's equations, these are the four most fundamental equations which govern all of electronics we see nowadays, from light bulbs to fans to electric motors to everything and generators. So let's first remove this thing. In order to understand what these four equations means, we have to first understand the vector calculus operators. These are the three vector calculus operators. This thing is called a grad or a gradient. This thing is a div or a divergent. And this thing here is a curl. So what these three things mean? So what grad really means is that how much a vector thing is changing in all three directions. And the div, this is one of the most important things in Maxwell's equation. The grad thing is not needed for understanding the Maxwell's equation. This div and curl is the really important thing. Div measures, let's say you have a source here, and this source emits or flows something. Div or divergence measures the strength or amount of flow is flowing. If that thing is going outwards or is outflowing, then the result of divergence is gonna be, I guess, plus. And if it's going backwards or inwards, then it would be minus. The div is defined as, here's a dot. Remember this thing. It basically means the dot product. And here's the grad thing. Grad is nothing but normal multiplication. But div uses the dot product here. So the dot product with div of a vector field is given by del of f in the x direction divided by del x plus del of f in the y direction divided by del y plus del in the z direction divided by d del z. This is the definition of divergence mathematically. We're not going to be using this. We'll just use it when solving for the Maxwell's equation, but I personally never tried to solve it. And let's move back to the curl. Curl basically measures the circulation of something, a vector. Let's say you have a vector which curls this way. Curl measures the circulation of this. More magnitude means more curl. And if this thing is clockwise or this direction, then curl is positive. But if this thing is anti-clockwise, then the magnitude of curl is negative. these two things are really important in understanding Maxwell's equation. So what our first equation was that del or divergence operator dot product electric field is rho divided by epsilon or E naught. I'll assume that you know basics of calculus here, and I'll also assume that you know high school or let's say middle school level physics. This E represents the strength of that electric field. And from this equation, we are seeing that, let's say we have a charge, let's say we have a positive charge. This charge is gonna have electric fields like this. Okay, that's just the div thing. As we see in there, it's moving upwards. And for a negative charge, this thing is moving inwards. This is exactly why we use this div operator here. And the electric field lines are pretty much spreading all the way up to infinity. Because you know the Coulomb's law uses the R square term where R has no bounds, it can go up to anywhere. And another thing to notice is that, or remember, it's called the Gauss's law for electrostatics or Gauss's law for static electric fields. And this thing, this charge here, let's call it Q. This charge is obviously static. That means it doesn't move at all. If it moves, then it will straightly go to the domain of electrodynamics, which we're not dealing with now. So what this side means, these two sides means, it means that the strength of that electric field's divergent behavior that flow outward, the strength of that flow is just the charge density of that region divided by some constants. It's, as I remember, called the permittivity of free space. Basically measures how freely that charge or electric field line can spread in a vacuum. These things, these lines are called electric field lines. So what we've seen here that more charge means stronger electric field lines and smaller charge or less charge means weaker electric field lines. This is just the first equation, and all of these equations are easy like this. I hope you understood this. And our second equation is also a Gauss law, but this time is a Gauss law for magnetic field. Magnetic field is always defined, most of the time defined by B. And surprisingly, this thing is just zero. How is this thing even zero? Doesn't that mean that magnetic fields don't have any strength? They're strengthless? Not really. What we've shown there in the first equation will bring up here again. Notice it's just a charge, a single charge. But as for a magnet, the magnetic field is like this. This goes up to a lot of space. And notice here that no magnets can have a monopole. There is no such thing as magnetic monopoles. You must have a south pole associated with the north pole. These two poles make a magnetic field. And here we are not seeing any divergence behavior. Divergence is what means like it's flow outward infinitely, but it's not flowing anywhere in this magnetic field. It's just going from this and coming back to here. That is why it's just zero. I hope you understood this as well. Let's move on to the third equation. And here begins the part of electrodynamics. And now we'll use the cross product with del operator or the curl here, and it's given by d of b by dt. And notice there's a negative sign. So what it means that, first let's understand what it really means. It's called the Faraday's law of induction. So Michael Faraday was experimenting with his magnets and he noticed a cool thing. His setup was like this. Let's say you have a ring of foil and a magnet. If this magnet goes inside this ring of foil or coil as we know, this magnetic field here will induce some electric fields from this foil. As it goes back and forth, we'll have some current. And that's what this thing is saying. Now remove all those unnecessary lines. Yeah. So if this thing is moving, remember what derivatives are. Derivatives are rate of changes. And this thing is changing its position after some time. This thing is going there. And in that process, when it comes inside this valve, it's going to give us some electric field. And that's basically the case in most electronics now we use. And you may ask, why is there a negative sign? The negative sign comes from the direction of that electric field. When this magnet moves inside this foil, it's going to create an electric field outside this foil. It's like, I'm just exaggerating this, it's like rings. It's like rings. Just like this. And the way or direction it circulates is this. The electric field is now circulating in anti-clockwise direction. This is usually described by the right-hand rule, I guess. And that's why, as we've seen earlier, that if we have an anti-clockwise circulation, it's gonna give us a negative magnitude of that electric field. And hope you understood why we are using the curl operator here. That electric field is circulating outside that foil. That's what Faraday found. And now we have the most important equation in all of these four, which is it's important but not the most important. It's just pretty complex. This and what's really happening here is that we have two components here. We've seen it nowhere in all those previous three equations, but here we have two components. What it really means is that the circulation of magnetic field can be created by this or by both. This J here, it's just the current. We always like to describe it as I, but it's not really I, it's the current density. Let's say you have a wire here and electrons are moving. And as electrons are moving, they're carrying electrical energy and creating an electric field like this. This is just basic electromagnetism, basic electrodynamics. As electron moves, they create an electric field. And as we know, if electrons are moving in this direction, current will move in this direction, the opposite direction. And what it means to move current is that positive charge, it's not actually positive, but pseudo-positive charges are moving in this direction. So what can we write here is that some pseudo currents are moving, or pseudo protons are moving this direction, and we have real electrons which are moving in this direction. Here comes the most interesting part. This is the phenomenon where special relativity and electrodynamics shakes their hand, as these electrons are moving. When they are moving from their frame of reference, these electrons won't be the same. They're gonna get stressed. They're gonna get compressed. So, as we seen earlier, for each proton there are each electrons. For each electron there are each protons. But now that's not the case. The charge is the same. Current is the same, but the charge density has changed. This J here is charge density. Oh, sorry, that's not charge density, but that's current density. So electrons are moving this way. And notice now there are some charge differences. Here are more negative than positive. These spaces here, these two sides, they are free from any protons. They are just bunch of negatives. And now this system now has some charge. And what it means to have charge? Charge just means attraction. And what causes attraction? It's just magnetic field. That's why moving electrons or moving current gives us some magnetic field. This thing is called Ampere-Maxwell's equation. This term was introduced by Ampere and this term was introduced by Maxwell. That's why you call it Ampere Maxwell's equation. This is the first part, or the Ampere's part. Now let's understand the second part. But notice here that these constants, these things are just constants. You don't have to worry about them. They're just chilling in the equations. And here's the second part. It's pretty similar to the first part where we've seen this equal to negative dB dt. And here we have the exact opposite thing. But that's not minus, that's a minus, that's a plus. It's just a little different, but the whole thing here is the same. The circulation of magnetic field can be created by changing this electric field. That's the same thing as we seen earlier, that current analogy. Electrons are just moving and chilling in the weights. Current is moving, electrons are moving this way, so current is moving the exact opposite way, and we're getting some magnetic fields. And as we use the proton analogy here, we're not going to be using the proton analogy anymore, because now we have electric fields. These each electrons, I hope you remember the first equation, have some static electric fields. But as they start moving, they create magnetic fields. We've seen that thing. They start to create magnetic field, and that's what this is. And these two things are just scaling factors. You can think of them like this. That's pretty much the four of Maxwell's equation. I hope you're not scared of them anymore. Yeah, this equation, these symbols look pretty much awkward and demonic, I said, but it's pretty beautiful. That's the topic for today's video. Hope you enjoyed it.